I think you're really excited to see what the results are. But before we go to the results, we first still have the solution presentation. And for that, I want to give the word to Ragnar.
Thank you. Yes, also from the jury, I hope you enjoyed the problem set. I hope you had a great time. I saw many, many balloons, more than the last few years in the contest area. That was super nice to see. So I hope you had a good time. We will all be presenting some of the solutions in order from easy to hard, or most solved to least solved. But before that, I want to just thank all of the jury members. Most of us, half of us are sitting in the front here. Some of us are walking around. We had a very large jury this year. I think 18 jury members, largest of, I don't know, maybe ever. It made much light work. That's very great. We also had a bunch of proofreaders from all over Europe. We also thank them for fixing clarity, making the problem statements more clear. So then I will start by explaining problem A, which happened to be the most solved. And so what you see in the top right of this slide is a timeline. Actually, this. So you can see that in the beginning of the contest, it was solved a lot, many accepted submissions, few wrong answers. I think purple is runtime error or time limit, I'm not quite sure. And then towards the end, there were a few more submissions. And this one is blue because it's in the freeze. And so we were given a list of up to 1,000 surnames, Dutch surnames, and we have to sort them. And I can tell you from experience that sorting surnames is hard. My surname has a space, Groot Koerkamp, and everybody calls me Koerkamp online. It's not great. So this problem is like very relevant. And so we're given these names, and we have to sort them starting from the first capital letter. And we don't have so many names in the input, so we can basically just use the standard n-log-n sorting algorithm from your standard library in whatever language with a custom compare function where you search for the first capital letter, like the first character between A and Z, and sort by that suffix. And so this runs in n-log-n. And there were 99 submissions, and before the freeze, it was solved by 83 teams, of which that's all but one. And the last team, I will spoil now, did also solve it in the freeze, so everybody solved problem A. Congratulations. And next up, Paul will explain problem J.
Yeah, thank you, Ragnar. So problem J was another easy problem, but you will see that the solve graph looks kind of different for this one. So in this problem, you were given these cranes, which are on some construction site. Each of them has some given position. Each of them has some height. And now you need to place these jibs, these horizontal bars on the cranes, subject to some constraints. So the cranes should not collide. The jibs should not be longer than the height of the crane. And then the ground area that can be reached is maximized. And then there was this figure in this problem statement which made this look insanely scary, like this is some very complex geometry. It turns out it's actually not. It's just the picture was sort of meant to mislead you. One, into thinking that, oh, this is very hard. And two, into the other part was that the solution is actually not unique, because you only need to maximize the area. What happens here is that there in the center you have this crane of height 6, which has radius 2, but could also have radius 3, and that would still be contained inside the area, so it doesn't change the total area. And that also caused a bit of confusion. It also caused a few questions to be answered, which we mostly answered with no comment, yeah. So, okay, so then how do you actually solve it? Well, I mean, you don't have to maximize all the radii, but it's certainly easiest if you do. And if you find the maximum radius, well, you just loop over all the circles. There's only 1,000 of them. And then, so you make each as large as possible. Yeah, then for each of them, you loop over all the others, over all of the other ones that are larger, because the smaller ones don't matter. And that's a runtime of n squared and is plenty fast enough to get accepted. Okay, I'll hand it over to Marte for...
Yes, thank you, Paul. So for the next problem, evolving etymology, you were given some word S, and you needed to make a new word from this word by doubling the word, just putting it after itself, and then take every second letter of that, starting with the first one. And you needed to do this up to 10 to the 18th times. That's a lot. So one observation that you can quickly make is that any method that applies this method like iteratively k or square root of k times will definitely be too slow because you don't have time to iterate over this word for 1 billion times. So we need something in order n log k in order to solve the problem. And we can do this using binary exponentiation. So what we can see is that after every time you apply this method, you multiply the resulting indices that you use inside the string by 2. So after some iterations, this character in this word becomes the index I times 2 to the power k modulo n, of course. And then this 2 to the power k can be calculated using binary exponentiation. Python, you have this fancy power method that does this for you. And then, yeah, that solves the problem. The fastest runtime you could get here was even n plus log k. If you calculate this binary exponent for all the positions. But you could also do this character by character, and then n times log k would also be accepted. This problem was solved 70 times before the freeze, and then there's still 23 pending submissions. And I will now hand it over to Andreas.
Right, so, why do we have L and not? Okay, then you do it.
Okay, limited library was supposed to be a fairly straightforward problem. We've got m books, n shelves, and we need to fit the books into the shelves. The first detail to notice is the books all have the same width, but the books all have a different height, and the shelves all have a different height. And then for each shelf, we can make a choice of 2 overall width. That is like how many books fit into that shelf, either X or Y. And we need to find the maximum number of shelves that we can shorten to the shorter capacity Y. And there are a couple of options you can make to convince yourself that greedily the shelves works. That is, you always try to fit a book with a given height into the shelf with the lowest height possible, and if that doesn't work, you just spill over to the next larger shelf. And if you think a bit further, you'll convince yourself that the number of shelves with low capacity Y is monotonous. So like if that works for k shelves with capacity Y, it also works for k minus 1 and so on. And that leads to a solution. We sort shelves by height, we sort books by height. Then you probably want a function that tries to greedily move books into those shelves, into k shelves with capacity Y and n minus k with capacity X. And then you can just binary search on that function for the maximum value of k. Before the scoreboard was frozen, 142 submissions, 67 accepted, and the rest we'll tell you later. Now on to...
All right, now to Dutch democracy. So we are given n parties and their number of seats, and we want to form a coalition in a parliament. So we want to form a special coalition, some candidate coalition, fulfilling 2 criteria. The first criteria is that the total number of seats of that coalition is larger than the overall total number of seats in the parliament. And the coalition should be minimal. That means that if we drop any party, then we have at most half of the total number of seats in the parliament. So we can do this by considering for each subset the lowest number of seats. And this will categorize this subset. And if we drop it, then it will, if it fulfills both criteria, then it will not be a candidate coalition anymore. And this will then, by transitivity, be the case for all parties in the subset. So what we do is we sort the parties by their number of seats, and then we do some dynamic programming that is similar to subset sum. So there are various ways on how to do it. One way to do it is we have some two-state TP where we include the currently smallest party k, and we consider the number of seats that are at least m. And then if you calculate this, depending on what transition function you use, you calculate the results in the end. And this runs in time number of parties times number of seats, which fits into the time limits. So we got 131 submissions and 15 were accepted. And let's see what about the 12 unknown submissions in the last hour. And one fun fact. So we called this Dutch democracy, but these criteria do not apply to the current government because it does not fulfill the minimality criterion. And another fun fact, up until recently, the German coalition did have fulfill both criteria, but since recently, they dropped the smallest party. So now it's only minimal, but not a majority anymore. OK, to the next problem, flowing fountain. So we are given a fountain where we want to pour liquids, and we have different levels that each have different radius, or like potentially same but various radii. And the liquid can fill up these levels, and then it will flow down into the next level that is larger than the current level. And we want to simulate this. So we can just do that in code, but this is too slow. So we have to be a little bit smart about it. So the runtime q times n does not fit the time limit. So how can we do this a bit faster? So for every level, we want to find the next level that is greater, strictly greater than our current level. And we can do this using a stack with some linear paths. And once we have that and we do the simulation, we can use some data structure like union find to track whenever one level overflows. And this will always be the case. So then we union the corresponding levels together. And one has to use path compression to make it in the time limit. So the runtime then is linear for the linear stack pass, and then q times Ackermann for the union finds. We have 140 submissions and 50 accepted.
Thank you, Andreas. So the next problem is Kreutknoten. I'm sorry, I don't know how to pronounce that actually. So we are given a bicycle network, and we have a certain number of stores, and they may sell Kreutknoten or not. And they do that with a certain probability. So we know for each store what the probability is that they do still have Kreutknoten. And the problem is to output the expected length of a shortest path if we want to get from vertex 1 to vertex n and to get the snack on the way. Right, so here we have an example. For example, if store 5 has Kreutknoten, so their shortest path is actually just the shortest path, which has length 3. But if store 5 does not have Kreutknoten, we have to go over store 3, which has length like 11, if I'm able to sum correctly. Right, so if we want to generalize the idea, so the idea is a store is better if there's a shorter path that visits the store. And we only get Kreutknoten at a store if it does have them, of course, and if there's actually no better store, no closer store for that. Right, so we need like two things. The second thing is the probability, but we start with the length of the path. So for each store, we need to compute the length of the shortest path if we actually visit the store. And this can just be done using two Dijkstra runs from vertex 1 and vertex n. Right. So now to evaluate how good they are, we have to sort the stores by their distance in ascending order, and like now we just assume that the best store is actually V1 and the worst store is Vn. Now onto the probability. So the probability that some store has Kreutknoten and no better store has them is, so we have P of Vk, which is the probability that the store itself has Kreutknoten, and all the better ones do not have them, so we just take 1 minus P Vi for all the previous ones. Right, and now just to calculate the expected length of a shortest path, we just sum over all stores and multiply the probability that it is actually the best store times the distance of the path if we get Koordinaten at that store. And the running time for those is dominated by the 2 Dijkstra runs, which is O of m log n. Right, and there are 102 submissions in total, 50 accepted, and 17 are still unknown. Right, I'll hand over to Ragnar.
Thank you. So next problem H, hash collision. So there was a long story here, but in the end, it boils down to you're given a function from 1 to n to 1 to n, where n is 200,000, I think. And you can query this f to the power c of r. And we want to solve this equation f to the power c of r equals c. So f, basically, you can see this as a graph. F sends you from one node to another node. So every function of every node has one outgoing edge that's given by f. And in a way, what you can see is that f to the power c of r equals c. We kind of put at c, and then walk c steps back and find r. So we want to find a node c so that we can take c steps back, and then just say we now take c steps forward from r. And so cycle of length m, we can walk backwards, because instead of going one step backwards, so m minus 1 steps forward on a cycle. So once we have a cycle and a point on it, we can just go the value of that point number back, and then we find a solution. So then the problem reduces to find a cycle, and one way to do this is, so we can just first go from a point n steps forward, because this graph always is guaranteed to have a cycle. If you go n steps forward, you will be in a cycle. And then what you can do is you can do the square root decomposition, where you first go very many steps forward, and then you first take s, where s is square root and small steps, and then you take s big steps, and then you will always find like 2 that are the same, and then between this you find the length of the cycle, and you can solve the problem. And this requires 2 s queries, and s is like 480, so it just fits below 1,000. And so around half the teams did this solution, and it's nice, but it's also kind of complicated. It's like 20, 30 lines of code. But actually, there's a solution. I think it's probably 3 lines of code if you do it efficiently. So what we can do, we can just take a point x, go 200,000 or n steps forward, and now we find a value c there. And now we're going to, so let's see is 23. We need to go 23 steps backwards. And to go 23 steps backwards, we can just go n minus 23 steps forward. And then we're done. So you just do 2 queries, a very far query, a slightly shorter query, and then the difference. And around half the teams did this, half the teams did the complicated solution, and a few teams tried like a randomized approach based on birthday paradox that sometimes passes, but it's like we had a lot of test cases against this. And so, I mean, it had quite a lot of wrong answers, but also quite some accepted. And Paul will go on with the next problem.
All right, problem C. So this was called Connect 5. And you did need to connect 5, namely 5 locations in this Manhattan-style city grid. And you needed to connect them in a specific way. So you needed to be able to get from each location to each other location along one of the shortest possible paths. So for instance, here between M and P, we go to the right and then up, and that is one of the possible shortest paths. And then this means we need the square there in the center. So you just don't have just a spanning tree, but some extra edges in some of the cases. So and you should do this in a total minimum length and output that minimum length. So one of the insights that tremendously helps cut down the number of cases one needs to consider in this problem is that, say there is a point that is to the very left, and it has the unique leftmost x-coordinate. Then we may just as well make a street that goes from there towards the right until it hits the second least x-coordinate. And then you can do, of course, the same thing from the bottom, from the top, and from the right. So, and the other thing is, if you drew that street at some point, then you can also just relocate that point of interest along the street. So then we have this new case on the right here. Now, to actually solve the problem, you can just repeat this action as long as that's possible. And this might cause some of these locations to coincide. In that case, you can just remove the duplicates, and that might free up more of these actions that you can do. And then if you analyze this enough on paper, then you realize that there's only 5 scenarios that can then arise. One of them is just a single point. In that case, you're done. The other 4 cases are depicted here below. So one of them is you have just a rectangle. One of them is a rectangle with 1 point on one of the edges. One of them you have a rectangle with 1 interior point. That's the rightmost case. And the one that's maybe tricky to overlook is the 3rd one from the left, which is this sort of pentagon-looking shape. But anyway, in nearly all of these cases, you just draw this rectangle. In the rightmost case, you still need 1 extra chord, and then you just draw the vertical or horizontal one, depending on which of these is shorter. So if you did it carefully, the amount of casework was sort of manageable, and 14 teams managed to do this before the freeze, but there were still 72 submissions during the freeze, so we will see how many joined those 14 teams in the end. Okay, I'll next hand it over to Khaled, I believe, who will talk about problem M.
Right, next problem. We have a convex polygon, and we take a uniformly random point from inside the convex polygon, and we are required to find the expected number of triangles from this larger polygons that contain this point that we just threw inside. Now, yeah, the first observation is that you can express the answer to of 0, 1 random variables such that 1 variable corresponds to 1 triangle, and it's equal to 0 if the point is outside, and it's equal to 1 if the point is inside. Now, when you do that, you can write the answer to the problem as 3 nested loops, and basically the sum of all the probabilities that this random variable is equal to 1. So you can have a cubic solution, right off the start. And then with some algebraic mastery and some tricks, you can reduce it down to O(n squared, as shown in the second line. And then you can notice that you can pre-compute a lot of these inner sums, and eventually you can just get a linear time solution. So that was it. You just need the right combination of probability theory, some very primitive geometry, and some expression manipulation, and you got it. Now, there were some catches related to precision and to overflow, basically. So even though the overall answer to the problem is less than, it fits inside a long, you most probably will have an overflow in your intermediate computations. That's one problem. Longs probably will not work. You will need to use 128-bit integers. Or you will need to use long doubles all the way, and that will get you the solution. 64-bit floats don't work either. Sorry? They do. Double passes, right. Double passes. Yeah, and actually you can infer that because of the limits of the problem. So the coordinates are 10 to the power of 7, not the usual 10 to the power of 9. And the margin for precision is a bit more generous than usual, so you can infer that. Now, an exercise to the avid reader. You can solve this problem when encirclements are not only triangles, but also arbitrary sub-convex polygons. It will be slightly more complicated, but you will arrive at a similar linear time solution eventually. And that's it. Next is, oh yeah, sorry, we got 12 accepted solutions and a lot of unknowns, and we'll see how that goes. B.
Okay, time for problem B, binary search. So binary search is a graph problem. You are given a graph with the n vertex. Every vertex. The problem is to find the length sequence that you count by walking around in the graph. So it looks pretty easy. It also thought to be easy, but it's actually hard. So first, a good idea is to ask yourself, when is the answer infinite? And you can draw some trees, for example, and see that it doesn't look infinite there. If you make a cycle and you put 0, 1, 1 on the vertices, that cycle, the answer is infinite. And the reason for this is, for any binary sequence you have, if you only walk on top of this cycle, you always have a choice. You always have a 0 or a 1 neighboring you. So, sequence. So for any graph that has the answer. Take the longest path of these 4 offsets, and it turns out that the answer is the shortest one of these plus 1. And the proof of this is, of course, the answer is always smaller than or equal to that, because the shortest one of those plus 1, if you just take that pattern, you can't get it by definition. It's not achievable, but any other binary string you can get. And you can get it basically by walking on top of this pattern 0011 and tracing like where you went and taking that segment and overlaying it on one of these 4 longest paths. So in the end, that's what you have to do. You have to find the length of the longest path of each of these 4 segments, and these segments, they contain a pattern that repeats every 4 times. So you have like 4 times n states. Actually, it's 2 times n, but yeah, so you can do it with a dynamic programming with 2 times n states or 4 times n or whatever you want. So in the end, the code is not very long, and this is mostly linear time. So the next problem is I. So I give it to Renier.
Thank you. Okay, so the next problem is I. It's a kind of magic. So in this problem, we need to count the number of multiplicative magic squares where the product is under a certain value n. So how do we do this? And basically the first observation is if we have such a multiplicative square, and we look at just the factors of some prime p in this square, and take all the powers, then this should actually form an additive magic square, but potentially with duplicates. And if you do some linear algebra on magic squares, then you find that there's just some form that all these 3 by 3 magic squares take. I won't go over the exact form here, but and using this, you can also just compute the number of magic squares, potentially with duplicates, with a certain sum. And note that the sum is always a multiple of 3. So what does this mean for multiplicative magic squares? Well, it means that the product will always be a cube. And And furthermore, we can just take this form and do things separately for every prime factor and multiply basically the number of these additives squares for every exponent in the prime factorization. Okay, so but now we have counted the number of squares with duplicates and we want it without duplicates, so we need to do some kind of inclusion-exclusion. And the idea is we can just look at all possible ways that there can be duplicates in the magic squares, and up to symmetry you find a couple of options. And for each of these options you can find a similar formula as to the one that was on the previous slides, by again doing some linear algebra or using the same formula again. But note that this again includes magic squares that have potentially more duplicates than is in the pattern. And then, well, we can do inclusion-exclusion, but maybe note that all these counts from the previous slides can be pre-computed using some prime seed in order n log n time. Where n here is at most 10 to the power 6 because the input was bound by 10 to the power 18. But because everything is, we are only interested in cubes, so we take the cube root of this. And then, well, inclusion exclusion, it gives you some kind of formula. It's not that important what it is right now. And now for every query, we just want to have the sum of all numbers of magic squares of all the products that are smaller than this value. So we take the sum of all these counts where m is at most the cube root. And we can basically just pre-compute this at the start of our program. And then in constant time compute the answer for every query. So this is one solution. There's also an alternative solution, which is maybe slightly simpler if you want. So there's only 300 different ways, or different prime factorizations basically, if we ignore what the actual primes are. So what we can do is just locally on your own laptop pre-compute for each of these possible prime factorizations what the number of magic squares is, and just hard code these 300 numbers into your code. And then you still need to do some kind of prime factorization in your code itself to use this to compute also all the other numbers. Okay, so this problem was accepted once before the freeze, but there were also 9 submissions after the freeze, so we'll find out later what happened to those. Then we move on to the final problem. Thank you.
So, grid is quite simple to explain. It's a generalization of the 15 puzzle. First of all, to bigger sizes, 500 by 500 boards. Game mechanics are quite simple. There's one empty square on the board. The rest are labeled tiles with numbers 1 to h times w minus 1. And you can slide any neighboring tile into an empty square. The other generalization is that some tiles are glued in place. Fortunately, they're in the correct place, but it limits the movement of all the moving tiles. And we made some guarantees to make it possible to solve that problem. We'll see about that later. That the moving tiles form a simply connected region. First of all, it's connected. Second of all, simply connected means there are no circles of moving tiles around a block of glue tiles. So all the glue tiles are connected to the border of the board. And one more thing that becomes important later is the problem only asks for yes or no, and not a detailed sequence or explicit sequence of moves. Now, first thing you need to do before even figuring out whether it's possible to solve or not is you decompose the moving tiles into bi-connected components, and you can figure that out if you play around with some sample cases that you can't move a tile across articulation points or cut vertices. And the articulation points are exactly what separates the graph into biconnected components. But within a biconnected component, you can always move around the tiles. And after you've done that decomposition, you just solve the puzzle on each biconnected component individually. A word of warning, you need to pay attention to edge cases. Due to the game mechanics where the empty square needs to end up, it's always, so for each biconnected component it always needs to end up on the topologically closest grid position, closest to the bottom right square where it finally needs to end up. And that means there's in each biconnected component there's one square that is a bit special, which you need to attribute to the right biconnected component, and there are a couple of possible overlaps where you need to pay attention. There's one example here, a 3x5 grid, and in fact it has 4 biconnected components, and one biconnected component of them, the pink one, consists only of a single square. The graph below is a graph representation of the moving tiles. The red nodes are the articulation points. Those single tile components become important. For example, I explicitly want to call that edge case out on boards that are 1 by x or x by 1. And you can also have that if such a narrow channel if big large parts of the boards are blocked out, include. Next thing you do after you've done the decomposition into biconnected components is you don't find an explicit solution, you just figure out whether there exists, if it's possible to exist, if it's possible to solve it or not. And you do that by computing the parity of the permutation that is defined by the labels on the tiles. And there are a couple of things to check. The permutation needs to be self-contained within the biconnected components, so no permutation across biconnected components because, well, you can't move tiles through articulation points. And we also required you to compute the parity in at most n log n time. Probably linear, which is easier than n log n, but n squared will not work. Finally, there is an alternate approach which leads to exactly the same results. Might be easier to see for some of you, just deducing from the game mechanics that the biconnected components are exactly those areas of moving tiles that you can flood fill with a 2x2 stencil. But then you still need to take into account those special cases of that one square that is topologically closest to the next biconnected component. And you also need to explicitly check that anything that is not in a flood-filled area is in the correct position. This problem was not solved before the freeze, despite having 70 submissions. If we did get the correct submission or not, you'll find out later during the award ceremony. Now back to Martin for some statistics and fun facts.
Yes, thank you, Arne. Right. So this graph looks roughly similar to yesterday, the language statistics. The only difference here is that we do no longer have a small bump at cockpit, but at C. So we had 12 plain C submissions, shout out to them. And we see a roughly similar division in acceptance and wrong answer between C++ and Python, only that C++ is used roughly twice as often as Python. Some more statistics. So we had many jury members this year, as I've now already mentioned, which means we also had many more commits this year to our repository, almost 1,000. So let's see if we break that magical boundary next year. We had 1,281 secret test cases, which is slightly less than last year, but still almost 100 per problem. We had 356 jury submissions or proof submissions in our repository, so many different approaches to solve a problem, many different approaches to not solve a problem, many different approaches to be too slow, etc. All really helpful. We did not do much code golfing this year. We did not have too much time for that, even though we had many people. But if you take the shortest jury solutions that we have for each problem, you end up at an average 18 lines per problem. And 2 of these were actually solvable in a Python 1-liner. Some more stats. So we have a lot of people, so we can do a lot of work. The test cases were actually finished on the Wednesday before the contest. I checked the Git repository. No more actual changes to the test data have been made since Wednesday, so I'm really impressed. However, the problem slides that we used for the live stream and solution slides were only finished today during the contest. So unfortunately, that's also all the stats that I have for you now, because normally we work on stats during the contest, but we did not have time for much more. So you have to do with this. And that's the end of the jury solution presentation, and then I will have a small intermission before the award ceremony.
For them. And for the last 3 years, the Gypsy also helped a lot. The committee that I spent now 6 to 7 years with, I think, an amazing time, amazing memories. And it was an honor to have the last contest that I'm personally involved with, to spend that with the rest of the committee. Thank you so much, guys, for all your hard work. It's incredible to see how it all went. So thank you so much.
We also have one very special committee member that we need to thank today, without whom none of this would have been possible, not this year, not previous year, and also not the year before. So I think it is a very good place to give a big warm applause to Natina, our contest director for the last 2 years.
Thank you so much. It was an honor to be involved for so many years. Then, before we go to the resolver, I have a few rules to explain. So first we will do the resolver for the company teams. So we will give them a warm applause, but the company teams won't be coming to the stage. After that, we will do the resolver for the contestants. The same rule applies for our first resolve. We will give a warm applause, but we won't come to the stage. We will come to the stage when you're team 1 to 12. Another thing is, if you're team 13, you won't be coming to the stage, but you will be coming if there is one institution in the 1 to 12 order, then you will be coming to the EUC, because from now on, only one team per institution will go to the World Finals or the EUC. We also have will do that. Alright, I think you guys have it under control. We have one more special guest for tonight, or this afternoon. But for him to come, we have to do something special. So can everyone with me say, woohoo! A little bit louder, I think. Do we see our special guest coming? One more time! Thank you so much for coming. And then I would also like to invite the other CHIPS team members and the company representatives to the stage. I see a Pavel coming. Do I also see someone coming from Huawei? Ah, yes. Woo! All right, then we will start with the result for the company teams. It has been a while that the company has achieved that, so good job, guys. So now we will go to the result for you guys, for the contestants. We're waiting for the OK for stream because we also want the people at home to enjoy the show. It's also still exciting. Is it like, ooh, is it going to work? Is it not going to work? Still see some waiting. Maybe our wise ball can do something fun. We have an okay. All right. So I see that you guys chose very creative names, some that I can't pronounce because they're emojis, or because they're like. Very creative. Let's see. Hey! We will be going a little bit quicker through the. Hey! slowing down now a little. Hey! Ooh-ah. So now we're in the top 20. Hey! What's three legs going to do? Bubblegum Vincent? Hey! Oh yes, very good name. Runtime Terror. Wow. Alright, we're nearing. This qualifies for EC. Congratulations! Alright, top 13. Ooh, hey! What's Unity going to do? Ooh, ah. But qualified for EC and first to solve problems A and F. Now we're going to medal territory. Team B is bronze medalist qualified for EUC and solved 10 problems in total. Please come to the stage.
Check.
Thank you so much. And try to move forwards. I think, yes. Bronze medalist, qualified for EC, and first to solve problem J. Congratulations. Thank you so much. Congratulations. Then for the 10th place, Friday volleyball. Congratulations. You can come to the stage. Yes, you're a really good coach of them. They also have a very nice mascot. Pizza-driven development. I approve of that. Sounds tasty. Ooh, hey! Hoover? I'm having trouble with pronunciation, but congratulations! We have a bit of a smaller stage this year, but we will make it fit. Thank you so much. Then we go to the second koper. Ooh, then we go to seems to be okay, will be okay. Ooh, but second chance. Ooh, and it's also then for the infinite loopers, I hope our resolver will not infinitely loop. Ooh, but congratulations with 6th place, infinite loopers. Thank you so much. Then for placeholder, will be a placeholder. Ooh, but congratulations with 5th place, placeholder. Thank you so much. Now we go to gold territory. Pizza-driven developments. Congratulations with 4th place. I think only for the name you already deserve gold place. Thank you so much. Then we go to third place. Seems to be okay. Well, to me, it seems to be more than okay. Congratulations! And you guys will go to the World Finals. Ooh. Thank you so much. Then for second place, zeg wat over. But congratulations, zeg wat over. Thank you so much. And then for first place, we already kind of know it, but congratulations, first place. Thank you so much. And then for one last ceremony, because as you know, this will be the last year that we hosted. But we have a new host for next year. And we already have some of them standing here. I don't know if more people will want to join here on stage. The organization of next year. It has been a while that we could perform this ceremony. COVID was happening, a few years went by, but it's a very important one. And that's the handover of the flag. Because a new organization bag. So there you go, guys. I think it will be an amazing next edition next year. And thank you so much for willing to organize it. And we can't wait to see how it will go. And that was the last edition in Delft. Thank you so much, all of you. Thank you for all the efforts, for the beautiful results, and I hope that you have safe travels home. Thank you.